Talking about sequences, and last time we had a fair amount of technicalities about just sort of the definition of sequences and especially the definition of convergence. We're going to try a bunch of examples this time. So let's, a lot of what we're going to be talking about is just sort of, here's a sequence, you tell me what it converges to, or maybe you say it diverges. So a common trick for sequences, if you want to do, lim n goes to infinity of a sequence like this. Like I said last time, you can usually use all of your same tricks from continuous limits of continuous functions as x goes to infinity. I would say the most useful one of these various tricks that you've learned, a common trick, would be put the n's in denominators. Put the n's in denominators. So I'm referring to, this is a trick which I'm sure you're familiar with, something like if I have 3n squared plus 2n minus 7 divided by 8n squared plus 2. Lim as n goes to infinity of this. It is a similar trick that you would use with continuous functions. Actually, you could use L'Hopital's rule on this, although it's not really necessary. I would say, following my little advice up here, put all the n's in denominators. I'm going to divide through everything by n squared. Everything on the top and everything on the bottom divide by n squared. That's because n squared is the highest power of n that I see here. So this will become 3. Well, I'll write this all out, but once you have seen this trick, you know what to do. I am dividing out by n squared everywhere. And because I'm dividing n squared on the top and the bottom, that does not change the value of the fraction. But then we can sort of cancel a bunch of stuff here. 3n squared over n squared is just 3. This one, I cancel one of the n's, but I still have one in the denominator. This one doesn't cancel at all. And on the bottom, 8 plus 2 over n squared. That's just simplifying, canceling the n's. And then we can do this limit by making the n's go to infinity. That causes anything with an n in the denominator to become 0. So this just becomes, when I do the limit, 3 plus 0 minus 0 divided by 8 plus 0. So the answer is 3/8. Right? This is the classic trick that you do when you have it's called a rational function, a fraction with polynomials on the top and the bottom. All right? You could, like I said, you could also use L'Hopital's rule in this example. It's not really necessary because you can do this trick instead. Here's a little variation of the same thing. Sometimes it can get a little fancier if you have, say, roots involved. Again, I'm going to try to divide through everything by the highest power of n that I see. I see really just n to the power 1 is the highest power of n that I see. On the bottom, there's an n here, which is inside of a square root. This n, I am kind of, in my mind, counting this as an n to the 1/2. It's not exactly n to the 1/2, but it's an n to the 1, but it's inside of a square root. So, but anyway, let's divide everything through by n. So this is going to be 3n over n, which will be 3 up top. And then downstairs, this really you have to think a little bit about how this will interact with the square root. But I just put 1 over n on the top and on the bottom. And now, in order to cancel on the bottom, I'm going to push the 1 over n inside of the square root, but that will turn it into a 1 over n squared. So this is, you just have to be a little careful about this. But up top, I just get 3. And then on the bottom, push that 1 over n into the square root, and once it enters, it becomes an n squared. So it's like this. All right? That's because 1 over n is the same as square root 1 over n squared. So when you move it into the square root, it becomes an n squared. And now I will cancel these guys down here in the same old way. This is lim n goes to infinity 3 over 1 over n plus 5 over n squared And then just like before, now I take the limit. Everything which has an n in its denominator becomes 0. So this becomes 3 over square root 0 plus 0. That, of course, is just 0 down there. And what's your interpretation of this? What's that?
Diverges.
It diverges. That's right. This sequence diverges. 3 over 0 kind of, when I see that, that means infinity. And so it diverges. Right? Any thoughts about that one? This one also you could use L'Hopital's rule with, although it's kind of complicated to deal with that square root on the bottom. I would do it this way rather than the L'Hopital's rule. All right? Excellent. Okay, one very important example, which I mentioned last time, is lim n goes to infinity. I mean, I kind of mentioned last time. -1 to the power n, all right? This one is a little tricky just because if you think of that like a function, -1 to the power n, and you imagine, like, what if I just like plug in infinity up here? The answer is like, I don't really know what that means. -1 to the infinity. If you write out the terms here, the terms, they are just, you would start with n equals 1. -1 to the 1 is -1. And then -1 squared is +1. And then -1 cubed is -1 again, and +1, etc. All right? So these terms, they look like that. And the question when I'm asking about that lim, the question I'm asking is, as you go down the list forever, what do these numbers get closer and closer to? Or perhaps they do not get closer and closer to anything. What would you say? I would say these numbers do not get closer to anything in particular, right? In fact, sometimes it's helpful to look at if we could sort of graph the sequence. This can be helpful sometimes, although your calculator is not terribly good at this, but I just mean, plot out these. It's not going to be a curve, it's just going to be individual dots. -1, then +1, then -1, then +1. Then you just go on like this forever, all right? I hope you agree when I say these do not approach anything. They just continue bumping back and forth. They don't get closer to any value in particular. So here, these do not approach any value. So the moral of the story is this lim n goes to infinity, -1 to the n, diverges. Remember, diverges just means it doesn't converge. When you say diverges, that doesn't mean necessarily that it goes to infinity or anything. These values definitely, they don't go to infinity, but we still say it diverges because that's just the opposite of converges. It doesn't approach a particular value. All right, -1 to the n, diverges. You cannot, I will mention again, I said this several times last time, you can't analyze this as if it were a continuous function, -1 to the power x, because that's not a real continuous function. An exponential function with a negative base is not a legitimate continuous function. All right. Now, something interesting is it doesn't, when you see this -1 to the n, like together with some other stuff, that doesn't automatically mean that it diverges. I mean, this one just by itself, it diverges, but check this one out. How about -1 to the n over n, right? Does this one converge or not? It's true, the thing on top does not converge, but since you're dividing by n, I mean, who knows what can happen then. This one, I think maybe it would be helpful to also plot the terms. The first term is -1 to the 1 over 1, so the first term is -1. The next term, using n equals 2, I'll get a +1 up top, and then 2 on the bottom. So the next term is 1/2. All right. If you think about it, what we're getting is it's just like 1 over n, only the signs are going to alternate, flip-flop each time. So the next will be a 1/3, but it'll be a negative, and then a 1/4, but it'll be a positive, and then a 1/5, but it'll be negative, and so on. Right? Those are the terms of this sequence. Does that converge to anything? Maybe it would be helpful to draw a little picture. -1 is the first value down here, right? Up here is 1. This is -1. Next is 1/2. That's like there, right? Next is -1/3. Just, I'm trying to do this well. Something like that. Then +1/4 is like this. These guys, I didn't like where I put that one. Something like that, right? They are smaller and smaller fractions as you go. It's just some are positive and some are negative. So they flip-flop in their signs back and forth. What do you think, though? Does this converge to anything, or does it diverge? What do you say?
Does it converge to 0?
It does converge to 0. Yeah, these numbers, they get close to 0. They are bumping back and forth in terms of the signs, but they are converging to 0. So lim n goes to infinity, -1 to the n over n. Actually, this equals 0. It converges. All right. This one's a little tricky to explain. Like if all I showed you was like this formula, rather than and you didn't want to think it through and look at the dots, how would you know that this goes to 0? So there's a little trick for this. If I really wanted to demonstrate this in complete detail, you could try to do the old divide through by the highest power of n, and then I would divide the top by n and the bottom by n, and you'd end up with the same thing again, which is not very helpful. Here's a little trick. This is a true fact. I'll write this as a theorem, although it's kind of weird looking, but actually obvious if you're thinking about it properly. It says lim n goes to infinity, an equals 0, if and only if lim n goes to infinity, absolute value an equals 0. If and only if is some mathematical phrase you've probably heard before. It means that these two things are exactly the same thing. Logically speaking, they mean exactly the same thing. It says if you have terms which are becoming 0, that's the same as the absolute value of those numbers becoming 0 in the limit. And the reason why this is true is just because, it is true. If something is approaching 0, then automatically its absolute value is also approaching 0. If it's approaching like through positive numbers, then these are the same already. The absolute value is the same. But if it's approaching through negative numbers, if it's going to become 0, then the absolute values will also become 0. And the other way around is true also. If you know the absolute values are going to become 0, then that means the individual numbers, whether they're positive or negative, are becoming 0 also. All right. So the fact that these two things are equivalent, what that means is, so to show that lim an equals 0, we can instead show that lim n goes to infinity, absolute value an equals 0. And I will just say parenthetically, this is usually easier. Well, I will say often. I don't know about usually. I know absolute values are kind of a pain to deal with. A lot of people out in these streets are absolute value haters. But actually, in certain situations, the absolute value makes the problem a lot easier. And this is one of those. So, for example, to show that lim n goes to infinity, -1 to the n over n equals 0, we can instead use the absolute values. So that would look like, instead, I'm going to do lim n goes to infinity, absolute value, -1 to the n over n. And then see if we can work with that. Is this any better? Actually, this is easier to work with. Anybody see something we can do to simplify or whatever? This one with the absolute values is actually easier to handle. Any ideas? Anybody remember your rules about absolute values? Actually, when you have absolute value of a fraction, you can just put absolute values on top and on the bottom. This is a legal simplification step with absolute values. Those guys individually, though, can simplify or something. Anybody say, what can we do on the top? I'm waiting for someone who hasn't said anything yet today. Thank you for your enthusiasm. Surely somebody can tell me what can you do on top there? These numbers are -1 and then +1 and then -1 and then +1. Yeah?
Just make it 1 at the end.
Yeah, it's just 1 to the end, which is just 1, right? These numbers up here, their absolute values are always 1, right? They're because each number is either a -1 or a +1. Yeah, actually, that's another rule for the absolute value, if you want to get real, ruly about it. Some people like rules. This is the same. You can do that with absolute values also. And this is, of course, absolute value of -1 is 1. And then 1 to the n is 1, right? So up top is just 1. What about on the bottom? Absolute value of n? You got to think about what is n here. N is like, it starts at 1, and then it's 2, and then 3, and then 4. Absolute value of n is just n, right? We can just ignore these absolute values. Now, I would say, like, in general life, you cannot just ignore absolute values, but this is legal because I'm talking about a sequence where n starts at 1, and then 2, and then 3, and so on. So this n is guaranteed to be positive. And so the absolute value of n is the same as n over here. All right. Anyway, what's this? This is 0, because n is going to infinity here. The limit of 1 over n is 0. All right. So I will say, let me just put a little note here. N, absolute value of n becoming n, this is because since n is positive. All right. This, of course, is not usually something you can't just, if you have the absolute value of something, you can't just change that into ignoring the absolute values. But in this case, because n is the index for our sequence, it's 1, then 2, then 3, then 4. These are all positive. All right. And so my conclusion is the absolute value of this equals 0, which means the original thing without the absolute values is 0. And that's what I wanted to be talking about. All right. Okay, one last trick. I'm trying to give various tricks for finding limits of things. One last trick, and this is something, I talked about lots of rules for limits at the end last time. This is one that I didn't put in that list, although it could go in that list. We can also push a lim, like this lim operation, lim n goes to infinity, inside a continuous function. So what I mean by that is something like, i.e., like specifically, if lim an exists and f of x is continuous, then lim of f of an is the same as f of lim of an. This only works if your function is continuous, but you are allowed to do that. As written, this looks kind of too complicated to be, it looks very weird to write a lim inside of a function like that, but actually this is super useful and we do it all the time. I think actually I've already done it a couple of times today and you didn't even notice, but this is actually a very natural thing to do. Here's an example, something like, this is just a very simple usage of this rule. What is lim of cosine of 1 over n? My basic idea is when I'm thinking about this limit, I don't really even think about the cosine part. I just think about what happens to this 1 over n when I take this limit. But actually, what I'm talking about is really, I'm thinking about it like this instead. Right? Just ignore the cosine. Really, all I care about is what happens to the 1 over n when the n goes to infinity. All right? And what is this? This inner limb is 0, because this is like 1 over infinity. So this just turns into cosine 0, and the answer is 1, because that's what cosine of 0 is. All right. So this is an example of pushing the limb inside of a continuous function. Like I said, this is something that you will naturally do without really thinking about it. But if you want to be technical about it, that is what you're doing. All right. I got a couple for you all to try. See what you think. So you're each time just find the limb, or say maybe it diverges. I got 2 of them. See how you like it. Talk to your friends if you like. You guys don't seem to talk to your friends very often. You're like an old married couple. Sometimes nothing needs to be said, you know? If you really love each other that much. Can I give a hint? This one, everybody's going to divide by some power of n on the top and the bottom. What power should you be dividing by here? Were you showing me the fingers?
N to the 5.
Yeah, I would say divide by n to the 5. Like I always say, you should divide by the biggest power of n that you see. Now, I don't see a 5. In fact, I see a 10, which is more than 5. But this 10 is under a square root. So really, I think of it as half of 10, right? The square root has the effect of cutting the powers in half. So I like n to the 5 for that one. Yeah, you're going to do the same thing. This moves it into the 5, and you're going to becomes the into the 10. The square root is power by 2. Okay. Yeah, when the 5, so
What?
okay. Yeah, that's good. So this one, when this thing goes. That's why you want to use it. Yeah. I know that's because something yeah. Yeah, so you can just say it's yeah. How's it going here?
Good.
Yeah. Have you okay.
Yeah, zero,
Something's weird about this. What did you do on the top and bottom? Can you divide it by n?
and squared. So
Oh, n squared. Yeah, I think you have too much stuff because it's not just. This is just one. Yeah. I mean, it's not. How's it going here?
Good.
Mm-hmm. How do you handle this?
I did that one. And then I did like a just kind of is that wrong?
One there.
Yeah.
It's not exactly wrong. So yeah, it is this.
Yes.
So
Yeah.
That's like
Second one didn't do it.
then
he's going to all this goes to zero.
Okay.
And then you have that. And then there's just a 3 that's sitting there.
Yeah, yeah.
So that's how you.
You don't have to everything. Because this is just a fraction. You can keep the fraction. No. So it was like in the fraction, just like it's like when you're like this, you're like here. When you're doing something, just like when you're doing something like 3 plus 4, 4 and 6, you're gonna simplify 3 and 6 or 7, 4 and 6. At least that's my
All right, can we talk about these? I see most people worked out the first one pretty well. The second one, it seems like everybody has the right idea, although it's a little weird to write it down properly. But anyway, for the first one, as somebody suggested, I'm going to divide the top and the bottom by n to the 5. So it'll say n squared over n to the 5 plus 3n over n to the 5 divided by square root. Well, I'll write 1 over n to the 5 here, and then what we had before. And now I'm going to push the n to the 5 into the square root. And the effect of that is to make it a n to the 10, or a 1 over n to the 10, when I move it into the square root. That's because the square root cuts the power of everything in half. So, simplifying up top, this is 1 over n cubed. This is 3 over n to the 4. And then on the bottom, it becomes n to the 10 over n to the 10 minus 7 n to the 3 over n to the 10. All right, and then one last step of simplifying. I got these guys up here. And on the bottom, square root. This is just 1 minus 7 over n to the 7, I guess. And now I take the limit. Everything which has a little n in its little denominator becomes 0. So I end up with 0 plus 0 divided by square root 1 minus 0. And this is just 0 over 1, which is 0. So the limit of that whole thing is 0. I hope you like it. Any questions about that one? People seem to be doing okay with that as I was walking around. All right, great. And this one here. So when looking at this, I think pretty much everybody realized that you don't really care about this or about the ln. Really, all that should occupy your attention is this part right here. Now, these are important. They appear in the answer, but they don't really affect the way that you think about the lim. This one right here, what's difficult about this is the weird alternating sign here, right? The plus 1, minus 1 thing. If you were to temporarily ignore that, it looks like just a rational function, and I should be dividing out everything by n squared. But if you want to think about this in particular, first of all, I would say focus on that part. So look here, right? This is the important part to focus on. The rest of it, the ln and the 3, they do appear as part of the answer, but really that part, that fraction part right there is what you want to focus on. And on some kind of intuitive level, I feel like if I divide through everything by n squareds, I'm going to get 0, because up top, well, on the bottom I'll have like a 1 here, 1 plus 0, but on the top I'll have a, if I did n divided by n squared, I would have 1 over n, which makes the top 0. But anyway, because of the alternating sign, I'm going to use the absolute values. So only addressing the thing on the inside, I'm going to take absolute values instead. Like so, right? And what's the purpose of taking the absolute values? The absolute values will basically kill that minus 1 to the power n minus 1. That's why I am considering the absolute values at all. So this is the same as up top, just absolute value n, and on the bottom, like that, right? Because the top there, taking the absolute value, that minus 1 to the n plus 1 is sometimes negative, sometimes positive, but when I take the absolute value, it goes away. It's always going to be positive. And now what's this limit? Now I just do the old trick about the divide everything through by n squared, which is what most people ended up doing. So this becomes dividing everything by n squared. N over n squared. The absolute values at this point actually don't matter at all. Would you mind, can I just say, sorry, before writing this step, I'm just going to get rid of the absolute values. N squared plus n. This is because all this stuff is positive, right? Exclamation. Right? N is, 1, 2, 3, 4, 5. And so n is always positive. And n squared plus n, whatever that is, it's always going to be positive because there's no minus anything. So we don't need the absolute values anymore. All right? And now the usual limit thing here. So I go n over n squared, and down here n squared over n squared plus n over n squared. Simplifying, we just end up with 1 over n on the top, 1 plus 1 over n on the bottom, and this is 0 over 1 plus 0, which is 0. All right? So that piece of it, its limit is 0, where I said, look here, that bit is 0 when I do the limit. So my final answer then, I'll just write it all again. ln 3 plus minus 1 to the n plus 1, n over n squared plus n. The only part that matters is that fraction on the inside, and we just demonstrated that that fraction's limit is 0. And so my final answer is just ln 3 plus 0. All right. I had to write this out in kind of two parts, and I think there is no correct way to write this just as one long thing. Sometimes you have to deal with a little piece of it separately on its own. All right. You might think, can I just do absolute values around the whole thing? The answer is no. It's not a terrible idea, I suppose, to put absolute values around the entire thing. But actually, the entire thing is not 0 as the answer. The answer is ln3. So you can't prove like this fact about the absolute values have the same limit as the sequence itself. That's only true when it eventually converges to 0. This one eventually converges to ln3. So you wouldn't be able to take the absolute values of the whole thing. All right, great. Thank you for your participation. I would like to talk about one super important example. Is called the geometric sequence. This is something that occurs all the time in real life. This is called the geometric sequence, and it is an equals r to the power n for some specific number r. All right? Some real number r, and that r could be anything. So I could be talking about, like an equals 2 to the n, or an equals, minus 1 to the n. Is this one that we've been talking about? Or an equals, minus 3 to the n, etc. Or something like an equals 100 times 1.05 to the n. That's a weird example, but actually this, you probably have encountered a formula like this. This actually is a formula you would use for compounded interest. If you start with, say, $100 in the bank and you get 5% interest for a certain number of years, this is not compound interest, but just like straight up, I call it simple interest, I guess. Interest, but not compounded. If you have $100 and you're getting 5% interest for 3 years, you would do 100 times 1.05 to the 3. That is compounded yearly. Anyway, you've probably seen something like this before. So all this to say, I said the geometric sequence is something that comes up all the time in real life applications. This is also the same thing that you would see in like population growth or decline. It's actually the same format as the little equation which describes my the iron level in my blood. Remember that little personal story, that little oversharing? So geometric sequences are super important in real life. That's all I'm saying. And my big question is, what about lim n goes to infinity, r to the power n? So does it converge? Well, really what I would like to know is, for which r does it converge / diverge? And furthermore, what does it actually converge to for the ones which it does converge? For which r does it converge? For which r does it diverge? For example, I can think of one where it diverges. How about n goes to infinity, 2 to the n? This diverges, right? Because the terms of this would be 2 to the 1, 2 to the 2, 2 to the 3. This diverges, right? This just increases forever. This is 2, 4, 8, 16, 32. It goes up to infinity forever. Can anybody give me an example of one which converges? Maybe you feel like it's always happened. It'll just increase forever no matter what the number is. Yeah? 1/2. Yeah, 1/2 actually converges. 1/2 to the n, right? So there are certain numbers. So this one looks like 1/2 followed by 1/2 squared. That would be 1 over 2 squared, 1 over 2 cubed, etc. And this converges to 0, right? Yeah. Is it possible for this to converge to something other than 0? Let me think of an example where converges to something that's not 0? Certainly it can diverge. It can converge to 0. Could it do anything else for another thought? Yeah?
Like 1 to the end.
1 to the end, yeah. Great. This is kind of a, if you don't mind me saying, kind of a stupid example because the terms of this is just 1, 1, 1, 1, 1 forever. But anyway, it does converge, and it converges to 1, right? So this one looks like 1, 1, 1. This converges to 1. All right. Are there any other possibilities? This is what I want to think about. Let's just look at this. So first of all, the big question is, for which R does it converge? We can, in general, look at, we can consider R to the power, well, how about if R is bigger than 1? I think this is an easy situation to consider. Then R to the power n. Actually, if you think about graphing the terms, plotting the terms one by one, this looks like a real valued function, R to the power x. If the base of the exponential function is positive, then it really is a continuous function. There are no problems. Remember I said there's issues if the base is negative, then weird things can happen. But if the base is more than 1, then this looks just like the function R to the power x. And that, the graph of such a thing, when R is greater than 1, always looks like this. This is the graph of R to the power x. It goes through 1 right there. All right? So, when R is bigger than 1, the terms go up forever. That's what this graph indicates. So, this means if R is greater than 1, then lim n goes to infinity, R to the n diverges. I will say it equals infinity. Right? These terms increase forever, and that's why it diverges. All right? So that is positive numbers greater than 1. All right? What about positive numbers but equal 1? I mean, this is the stupid example we already talked about. If R equals 1, then actually R to the n is just the same as 1 to the n. It's just, the sequence just looks like 1, 1, 1, 1 forever. All right? So that means lim n goes to infinity, R to the n equals 1. If the R equals 1, then it converges to 1 because the whole sequence terms is just 1 every time. All right? That's supposed to say if at the beginning there. If. All right. What about if R is, so if R is 0, a similar thing happens, it's just you get 0 every time, right? If R is 1, you get 1 every time, and it converges to 1. If R is 0, you get 0 every time, and it converges to 0, so I'm going to write that too. If R is 0, then R to the n equals 0 to the n, which is always 0. So the lim n goes to infinity of R to the n equals 0, all right? I'm trying to summarize all the various cases that we have discussed already. What about R between 0 and 1? If you look at what we've discussed so far, at the top you see R greater than 1. We also have R equals 1, also R equals 0. What about if R is between 0 and 1? So I would write it like this, 0 less than R less than 1. All right? What this means basically is like R is a fraction, 1 over 2 or something like that, 3/4 or something like that. Then R is a fraction. We could write something like R is like 1 over A or something like, it's just something which is between 0 and 1. This A could be any number bigger than 1, and that makes a fraction here. But what that means is then r to the n would be the same as 1 over a to the n. And here's a little trick. This is the same as just straight up a to the negative n. So what I'm saying is, if the r is a fraction, then actually what you're talking about is like an exponential function with a negative exponent. And that, the graph of that, is just like the graph I drew before, but reflected horizontally. That's because I have negated the exponent. And if you recall, that's what happens on a graph. If you negate the variable, this looks like a to the power minus x. A to the x would start low and go up to the right. A to the minus x is the sort of horizontal reflection of that picture, which makes it look like this. And so what's the lim here? This one, the limit is 0. All right, so I will summarize. If 0 less than r less than 1, then the lim n goes to infinity, r to the n is 0. It's because you're looking at terms on a graph that go like this, and they approach 0. All right. Have we said everything, all the various possibilities here? Not quite, because I didn't ever talk about negative values of r. We talked about r bigger than 1, r equals 1, r equals 0, r between 0 and 1. So this actually covers all positive values for r. What about the negatives for r? For the negatives, well, it's very similar. So if r is between -1 and 0, then you can do this absolute value business. So in this case, lim of r to the n, if I take the absolute values here, this becomes lim of absolute value r to the n, which is 0. That's because if r is a fraction, a negative fraction, then when I take the absolute values, I get a positive fraction here, and I already said that is 0 for this case. So if r is a negative fraction, you get 0. If r is a negative, we already talked about 0. What about if r equals -1? This is a case that we've already discussed. If r equals -1, then it's -1 to the n, which diverges. Right, -1 to the n, it's like we started out today talking about that. That diverges. And what if r is negative and more than -1, like more negative than -1? So if r is less than -1, again, by the absolute value thing, sorry, it's not by the absolute value thing, but it's then the this is a negative number to extremely high powers. This is going to diverge also. Then r to the n diverges. That is to say, it's a negative number to higher and higher powers. All right. This one actually doesn't become positive infinity because it depends on if the n you're looking at is positive or negative. It's either going to be a super big positive number or a super big negative number. But anyway, it diverges. All right. This is a lot of business that I just said. Can we summarize this in some way? I'm going to write this as a theorem. So this is a summary of all of that stuff that I said up there. It says, for the sequence r an equals r to the n, I'm going to summarize everything that we just said. If r is greater than 1, then the lim of this sequence, r to the n, equals infinity. It diverges and the terms become larger than any number you can imagine. All right? That's the first case. The next case, if r equals 1, then lim n goes to infinity, r to the n is 1. That's just because every term equals 1, and so you get 1 for the lim. All right, then we had, the next case was if r, actually this is summarizing several of what I described above. In this case, the limit is 0. This is for fractions because higher and higher powers of a fraction tend to 0. Whether it's a positive fraction or a negative fraction, or if you just start with 0 every time, you're going to get 0 for those limits. And then finally, the last case, if r is less than or equal to -1, then it diverges. All right. This doesn't really have a name, but this is the theorem about geometric sequences and what they converge to. All right? And I'm describing every possible thing that R could be and what happens in each different case. All right? This is super important. I would say you should kind of have this memorized. I don't know. It's not so hard. In my opinion, it's not so hard to remember this. Really what it's saying is if the R is big, then when you take powers of that, it becomes infinite. Or if the R is like big to bigly negative, as our president might say, if R is bigly negative, then again, when you take the powers of that, it diverges. It doesn't converge to anything. But if the R is small, like a fraction, it converges to 0 because higher and higher powers of a fraction just continue to get closer and closer to 0. And then this is kind of like the stupid special case. If it's just 1 every time, then it's just 1 every time, and it converges to 1. So this looks like a lot of information. To me, it's not so hard to remember these things. All right? The geometric sequence. We're going to come back to this. Actually, this will be super important when we talk about series eventually. So I would say remember this, and at the very least, put a box around it or something. We will be referring to this in the future. All right. We have about 20 minutes remaining. There is something else that I want to say about sequences. This is one of those things that seems kind of simple on the surface, but I want to talk about increasing and decreasing sequences. Increasing and decreasing sequences. These words, increasing and decreasing, they mean what you think they mean. A sequence, here, I'll write the definition here. A sequence, AN is increasing if what I mean to say is increasing, it just means that the terms, if you were to write them out, they just keep getting bigger. Something like, 1, 10, 100, 1,000, 10,000, etc. This is increasing, right? They keep on getting bigger. Can we give me like a kind of a? I want to say that in a more technically appropriate way. I don't want to just say they keep getting bigger. Can anybody say this in a nice way? Yeah, like this. She said, this is exactly what I was going to say. AN plus 1 greater than AN for each n. Excellent. Yeah, that means the next one is always bigger than the previous one, the one that came before, right? That is what increasing means. Sometimes this is referred to as strictly increasing because I did not allow for it also to be equal. So increasing means everyone is straight up bigger than the one that came before. They're not allowed to be equal sometimes. Yeah, excellent. So that's what increasing means. And what does decreasing mean? Decreasing, means the opposite. AN plus 1 is less than AN for each n. That means I wrote inch with an N inside that word, inch, for each n. All right, this is like people who talk about length and width and height. I don't know, does that annoy anybody other than me? There is no such word as height. Height is the word you're thinking of. Length and width and height. Yeah. It's height. Somebody said that a few days ago in the hallway, and it's been annoying me ever since. I've just had to say it publicly. I made a spicy social media post on the subject. Follow me on Blue Sky if you want to see my hot takes. Anyway, this is what decreasing means, all right? For each n, that an plus 1 is less than an. And here's a word, so these are, I'm sure you already know these words. Here's a word that perhaps you have not seen before, but the word is, we say a sequence is monotonic when, this is a weird word, but the meaning of this word is very simple. It's either increasing or decreasing. In either case, we say the sequence is monotonic. You know, in ordinary language, when you say this word monotone, it kind of means like somebody, usually you say this like somebody's voice is monotone, means they're just like everything they say sounds the same or something. In mathematics, the word monotone usually means the thing always does the same thing. So either it always gets bigger every time, which means increasing, or it always gets smaller every time, which means decreasing. In either case, we call it monotonic. All right, it just means either it's always increasing or it's always decreasing. You will see some homework problems about increasing and decreasing. I got one example, and then I will invite you to try one. How about show that 3n over n plus 1 is increasing? All right. Now, there's one bogus way that you could answer this question and one appropriate way that you could answer this question. Can I write the bogus way first? Nobody write this. And don't ever write this in the future, but here's the bogus way to answer this question. You would just, let's just write out the terms. I would start with n equals 1, and it would say 3 times 1 over 1 plus 1. That would be 3 over 2, right? And then the next term would be 3 times 2 over 2 plus 2. That would be 6 over 3. The next term would be 3 times 3, which is 9, over 3 plus 1, which is 4. I'll just write the next one. N equals 4. It would be 12 over 5. All right. Are those increasing? If you used your calculator, 3 halves is 1.5. 6 over 3 is 2. 9 fourths is like 2 and a fourth. 2.25. 12 over 5 dividing by 5 is like 0.2. So this is 2.2, right? No, 2.5. Yeah, dividing by 5 is 2.4. 2.4, yes. What do you say? Increasing, huh? This is the bogus way. You write them out and then you say, see, it's increasing. See? My response to that would be, well, what about the next one? You could say, oh, well, look at this, professor. You write out the next one. See, it's increasing. I would say, okay, well, what about the next one, huh? You can see where this is going. Here, you are not actually proving to me in general that this will always be getting bigger. You're just like doing a few of them and saying, huh? How you like that? This is not good enough, all right? So this doesn't actually demonstrate it for all the terms. This doesn't demonstrate for every term. It's just like the ones that you decided to write down. And that is not good enough. You need to demonstrate that this thing is increasing for all of the terms, all right? How do we, so this is the way that we are not going to do it, so don't do that. We should instead use the definition and prove that it is true. All right? We're not going to write a whole abstract proof with a bunch of words. If you know what you're doing, the proof is fairly straightforward. You just have to do a bunch of business. So there is one thing that's sort of important in how you write this out, but I will say it like this. We want to show that an plus 1 is greater than an, right? That's the definition. This is the meaning of the word increasing. An plus 1 is greater than an for any n. Can we actually demonstrate that? Well, yes, we can by plugging in here. So I'm going to plug in. This is the same as, all right, and here is the step which gets it all started. I'm going to write down this inequality again. On the right side, I see just an. So it's like something greater than, and if you recall, an is 3n over n plus 1. So I'm going to put an over here. And on the left side, I'm going to put an plus 1, which means you use this formula, but instead of n, you use n plus 1s. So it's going to say 3n plus 1 over n plus 1 plus 1. Right? On the left is what you get if you plug into the sequence using n plus 1 every time. And on the right is just the sequence using n every time. All right. And we have to demonstrate that this inequality is actually true. All right. How do we do that? I'm going to just simplify over and over again and hopefully end up with something which is obviously true. So I'm going to say this is the same as, all right, how would we simplify? First of all, I would distribute on the left side, distribute the 3 up top, and then on the bottom, you can just add them up. N plus 1 plus 1 is n plus 2. So this will say 3n plus 3 over n plus 2 greater than 3n over n plus 1, right? And then that is the same as, anybody want to suggest? What can we do next to simplify here? Yeah? Cross multiply, she says. I like that idea. I'm going to multiply across like this and like this. Although you should be a little cautious about this. Well, here's what I'll write. 3n plus 3 times that denominator from the other side greater than 3n times that denominator from the other side. Right? This is the cross multiplication. I don't know if you feel good about this. This is something perhaps, have you ever done this before? Like, are you even allowed to do that with an inequality sign here? With an equal sign, sure. With the inequality, I don't know, I feel like, my mommy taught me, you can't do everything with the inequality, and you got to be worried that sometimes you should turn it around. Like, should I have turned it around here? Any thoughts about this? Sort of the first rule of Fight Club is you turn it around when you multiply both sides by a negative number, right? That's what makes you turn it around. I would say this cross-multiplying procedure, really what it is I multiply both sides by this denominator, and I also multiply both sides by this denominator. And those two denominators are always positive. That's because n is a positive thing. This is a sequence I'm talking about. So those two denominators are always positive, which means I can multiply both sides by those denominators without changing the direction of the inequality sign. So this step is legal. This actually is not legal if these were continuous functions, like with x's, where the x might be negative, then this would be a bogus step. But because everything that I'm talking about is positive, this is actually a legal step. All right, can we continue from here? I don't know, if you can see where this is going yet, but I would, even if I don't know where this is going, I would distribute out this stuff. Yeah?
Factor out the 3 from both sides.
Yeah, all right. Yeah, you could do that. Actually, I wasn't going to do that, but yeah, you could factor 3 out. All right. I like that. If you factor 3 on the left, I was going to do the FOILs, which I suppose we can do next. Yeah, and then you can cancel the 3's. All right. Anyway, let's do the FOILs here. So on the left, it's just that thing squared, n squared plus 2n plus 1. On the right, n plus 2. Okay. Am I getting anywhere here?
Wouldn't it be n times n plus 2?
Yes, yeah, I didn't distribute. N squared plus 2n. That's what I was supposed to be doing in that step. Okay? Let's move everything over to one side maybe, or just like in this case, I think we can straight up cancel n squared on both sides, right? And also 2n. And this says 1 greater than 0. I think we're done at this point, although what does this even mean? Like, can anyone interpret this sequence of events? You certainly, whatever this means, you're not going to go any further than that. I will say, this is true. What that means, though, remember where we started? I'm going to try and zoom in here, zoom out a little. We started with this, and my proof said this is the same as this, which is the same as this, and this, and this, and this, and this, and this, and this is true. That means the original thing is also true. That's the whole point of all of this, all right? This is true, so that means an plus 1 greater than an is true. The end. Shun. All right? When you're writing a little proof like this, you have to at least write some words here to make it clear that what we start with is actually what we want to show. If you don't, I know there are some, especially in math classes, there's some people who are like word haters. Like, I never want to write a word in my math homework. My advice to you is get over it. Mathematics is done using words. This is what you want to show, and at the end we end up showing that what I wanted to show is equivalent to this, and that's true, which means the original thing that I started with is true. If you don't write any of these words, then it looks like you're beginning by assuming what you wanted to show, which is a bad news when you're writing a proof of something. All right, so it needs to be at least most of these words that I wrote need to be in there. All right, I got one. We got 5 minutes. Can you try one? I would like for you to show n over n squared plus 1 is decreasing. And that'll do it for today. Start off by writing what you must show, and then simplify a bunch of stuff. And hopefully you end up with something which is obviously true. Yeah. This is not it should be n plus 1. Can we talk about this? Sorry, I know I didn't give you enough time really, but we gotta go soon. So we want to show like so. Make sure you plug everything in right. I'm going to say this is the same as n plus 1 over n plus 1 squared like that plus 1 less than n over n squared plus 1, right? This is the same as this. Can I just say, if you got this far without writing any words, I don't like your answer. You have to write some words to indicate what it is you're trying to show versus like what you already know is true or something like that. Don't just write the equations or the inequalities. You've got to write the voids. All right, to simplify, let's expand out, like do the FOIL in the denominator on the left side. So this is the same as n plus 1 up top, and then square that out and then add 1. I think you will get n squared plus 2n plus 2. N over n squared plus 1, right? Now do the cross multiplying. I'm doing this a little quick just because this is, I saw folks were doing good here. Do the cross multiplying. N times n squared plus 2n plus 2. Do all the distributing here. This is the same as n cubed plus n squared plus n plus 1. That's what you get if you do the FOIL on the left. And on the right, distributing, n cubed plus 2n squared plus 2n. All right? And now I'm going to cancel as much as we can. The n cubes just straight up cancel entirely, right? The n squareds cancel a little bit. The one on the left can go away, and the one on the right is just going to be 1n squared. And the n's, similarly, I think I will be left with 1 on the left, and then subtracting n squared and n gives me n squared plus n. Like that. I think this is what you get after simplifying, canceling what you can. All right? You can't go any further than this. You should ask yourself, is that actually true? Is it true that 1 is less than n squared plus n, no matter what n is? The answer is yes, because n is, is part of a sequence. N is like 1 or 2 or 3 or 4. This is always more than 1, all right? So I end by saying this is true. If you want some justification, you could say since n is more than 1, right? Which means when you do this and add it together, you get something, actually that's more than 2 on the right-hand side. So that means an plus 1 is less than an. All right, there you go. See you next time. Let me know if you got homework questions.